So we start some lecture here first, and then after 45 minutes, we start the quiz, right? Okay. So now, 2 days ago, we have been talking about the power weighting. I just go through really briefly about that. So all the batteries are connected with the AH and also its voltage. So that's why we can use them to calculate the power weighting or WH for the battery. So here you can see there's common battery pack for EV. You can see that there's some popular one, like Tesla Model S. The configuration will be like that. All the charge sheet they embedded with this kind of the battery system. Now the Porsche one, the latest model one, that's how they pack that. You can also see that the high voltage cable are using this kind of orange color for this international standard. And BYD, they have been really famous about their brain battery, which will be like that. They saying that their current density will be even higher. So now there are some people saying that they can able to charge their battery within 5 minutes. So again, that's an issue of the how good to supply the power. We don't have that many power sources. So here we also discuss how we calculate the WH. So simply about the voltage multiplied by the AH, the coulomb. And then we also discuss about the charging current, usually using 0.2 C for the charging. For lithium-ion battery, that can be 1 C to 2 C. But usually when we're testing the standard, we're using 0.5 C. So here with some simple calculation, how we work with the rate of charger by looking into the current. Obviously, you can see that if you want to have a high C to charger, then high current, then you try to be much heavier. So in the future, if we want to have a really ultra speed, super speed to charge, then the power requirement will be really high. So this tutorial is just talking about how we manage the battery with different gradient for the row. I mean, it's a very simple calculation. So next, we also talk about the battery balancing. The battery balancing, as you see that here, we try to make sure that all the battery cells will have equal voltage against each other. So that's to ensure that the power for each of the battery cells will be equal. So usually the battery are connected in series, so the current must be equal, but the voltage can be different. So in this case, if you do have a battery balancing method, sometimes we call it the equalization. Make a pen, how to. Sorry. Equalization is another term we usually use for BMS. That means same as the cell balancing. So that's a very common term. So all the BMS, with the battery balancing, we try to ensure that all the cells are equal. In this case, if all the voltage are equal, then we don't have any particular cell become overcharged or over decharged. If the voltage are different, maybe some cell have low voltage, some cell high voltage. When we charge and decharge them all together, some of the battery cell may be overstressed, may be overcharged or undercharged. That's the issue we don't like to be. Once any battery cell become overcharged, then one particular cell will become over temperature. So that's also the issue we don't like. So once we have the capability to do the cell balancing, we can eliminate most of the problem. But how to do that? Then we do need a sensor to sense the battery voltage, ensure that each voltage will be quite equal. And sometimes we've got the whole pack to measure voltage. Sometimes we see a battery pack will measure individual voltage for each of the cell. As you know that one of the battery pack, they may have a few battery connected in series. So we do need to have some voltage sensor. So here we have one example. We are using some kind of the simple method to transfer the charge. Like in the first case, we are using passive. Passive means we're using resistor. In case any voltage or any cell is over higher than the others, we just turn on the switch to discharge its energy there, so that once the voltage becomes equal to other, we stop. Obviously, you can see that this method is so-called passive, because it's using the energy dissipation. It's not really balancing. It just protect the voltage from being overcharged. So that is to say, you can trigger it when to turn on. That would be something also this would be quite critical. But for instance, we use to set them as say 4.2 volt. In case any one of the cell approach to 4.2 volt earlier than all the other cell, we turn the switch to discharge it until this voltage equal to the rest of the cell. So that's why this is called a passive balancing. If you want to balance the cell earlier voltage, for instance at 3.9 volt, then all the cells supposed to 3.9, one of the cells become 3.94, probably we have difficulty to balance them because the set point to trigger the switch to turn on for balancing, you cannot have variable voltage. You can still do that, but that would more complicated control. So usually this kind of passive control only to help you to control the balancing at the top voltage. Another voltage will be like this using capacitor. So you can see that we can using different arrangement of the switches so that we can copy this capacitor voltage to here, or copy this battery voltage to here, and then this to copy back to here. Now using this kind of the so-called copying, not really copying equalization, then we can make sure that all the battery voltage will be equal. But doing this method is a little bit slow. If you want to balance the voltage from this battery back to this battery cell, because it's quite far away, so we need to this one connect to here and this connect here and so on. It's some kind of ladder kind of the delay anyway. But as I said, the frequency of switch here will be really, really quick, talking about say 20 kilohertz, maybe 100 kilohertz. So it only take you 50 milliseconds or so to transfer the charge. So even though they are slow, but still really fast anyway. So within seconds, all the battery cell can be balanced. But one thing we need to look at will be if these two voltages are not equal, when you turn on the switch, there will be voltage transient because we try to short circuit this voltage with that one. For instance, if the voltage is 3.9 volt, this 3.8, this 0.1 volt will be looping in here. So the transient current depends on the loop resistance. So that means if too much different, the transient current can be quite high. So what we try to do will be we try to balance it. Once we see a little bit voltage unbalanced, we can start to turn on the switch. So that depends on a lot of the control method. So you can see that basically the passive balancing using this one. So we have set point here to say what kind of limit we start to turn on the switch. So the resistor will connect to individual voltage cell. So for instance, we set the 4.2, once you see any voltage more than 4.2 volt, then we turn the resistor until the voltage go back to the rest of the voltage. So that's how we do that. So you can see the control is simple, easy to operate, really reliable because this circuitry is basically electronic. So don't need very complicated control manner, don't need a lot of the data management. So that's why this method has been used for most of the BMS. I think in the market, more than 95% BMS are using this one. Obviously, you can see that this is no good because the power losses. We don't like that. So but however, because so reliable, all the people are using that. So of course, there's another method called the active balancing. So you can see that this circuitry, I think I showed you last time about so-called the buck-boost converter. Do you still remember the operation for buck-boost converter? So the buck-boost converter, basically, you can see that if you turn on this one, the charge will looping in here. Turn on this one, this charge will looping in here. So you can see that this voltage will therefore deliver some energy to this voltage. You can see that in case this is a battery, this is also a battery. Then it looks like we transfer the charge from this battery through the inductor to this battery. So that's to say you can imagine something like that if you got battery in here. We're just using a switch to simplify my drawing for the MOSFET, right? This is resistor. So you can imagine that if that is our capacitor, look just same as battery anyway. So that's how, but this is reversed. It's reversed, so that means I can draw the battery in another way. So that's how it looks like. We transfer this one to here. When it turn on, the charge will go to here, and the charge will go to here. So the charge will go from this one to that one. You get that? I think we learned it 2 weeks ago, right? So now then, if you want to have balance, so you put this one in here. So what you can see will be like that. Now we put this one at the bottom, like that. And then we have inductor here. And then we have the switch here. Like that. And then we have diode here. Exactly the same. So we coil on charge in here, then the charge will go back to here, right? So that looks like a battery connect in series. Yeah. And then we draw it better again. Of course, there's a MOSFET. You see all the power MOSFET have its own diode inside. So that is electrically. So this one looping in here, and then we use this one looping here. So vice versa, if we want to balance the cell from here back to here, so what we need to do, we do the same. Then we can loop in here, and this current will therefore pass through, go back. So then the charge will move from bottom to the top. So basically, we're based on the buck-boost converter to do the job. You don't need to understand detailed operation for the buck-boost converter, but we're using this transistor method to deliver the charge between two of the cell. So if we draw them, will become just like that. So two of the cell here, we're using this arrangement, then we can transfer the charge from this to that one or this one to that one. If you got many of them, we can extend this circuitry to many, so that you can able to the whole thing. You can transfer the charge. So the good thing of this one will be, in theory, we have low power losses because the MOSFET and diode have a little bit of losses. So it doesn't like the resistor, all the losses will disappear. So that's why so this method only have 5% of BMS are using it because still need a lot of the investment in the MOSFET, control and balancing. One thing you can see that if you know that for buck-boost converter, I think I showed you last time, for buck-boost converter, output over input voltage equal to D over 1 minus D, the duty ratio for the transistor. So you can see that if you want balancing, I want these two voltage equal. When the voltage become equal, when D equal to 0.5. So that's to say, if I make these two transistors to 0.5 duty ratio, 50% on, 50% off, and vice versa, automatically these two batteries will have equal voltage all the time. You don't need to do that, you don't need to control, just tell it to turn on half the time. You can see that all the battery string in the whole series become 50% duty ratio, then they all equal voltage automatically. But in case you find that this one, the higher voltage than that one, you just turn on this slightly more than 0.5, you transfer the charge to here. So using this method automatically, even though you don't control it, you can able to obtain equal voltage, so-called the self-equalization. Do you get that point? So this circuitry, we call it buck-boost converter, or I think other people may call it flyback converter for those buck-boost converter with a transformer. So buck-boost converter is really famous topology, and this cell balancing also is really famous topology in all the BMS. So you should able to recognize the circuitry. So here will be another interesting tutorial. Look into that. And so the tutorial will be something like, look, if we have a series connected battery system, then all the battery are measuring at 4.14 volt. But we suddenly found that one of the cell is 4.2 volt. So we like to use the active balancing, no, passive balancing, to use a resistor to balance them. So move back the 4.2 volt back into 4.14 volt. So that obviously we can using a resistor to discharge the 4.2 into 4.14. So the time for balancing, anticipated time would be 1 minute. We want to do it within 1 minute. Finish the balancing. Then if each battery cell is 10 Ah, so what do you think the resistor will be needed for the balancing? How do you calculate that? Okay, so we assume that the battery cell will be usually from 3 volt to 4.2, fully discharged 3 volt, and fully charged will be 4.2. So what do you think the calculation? You think about it for a few seconds, then we talk about the answer. So in here, we got a few methods to manage this method. Just share with you how we think about this part of method. So one thing is, what we need to do is to use the resistive balancing to discharge the 4.2 volt to 4.14. Only you can see that usually the voltage unbalanced only means tiny voltage. We not try to balance huge voltage because our sensor will monitor voltage continuously to use unbalanced only 0.01. In here, let's make it more saturating, say 0.06. So in 1 minute. And then you can see that how much energy we need to remove. So one people was trying to say, one student trying to say, the 4.2 volt minus 4.14 multiplied by the charge, that is the energy need to be removed, 0.6. Okay. And then this energy, 0.6 multiplied by 360 seconds, right? We convert hour into second, this becomes joule. And then this will be V square R is the one we calculate the resistor R, right? And T, the charging time is 1 minute, 60 seconds. So 4.17, I use a midpoint because the voltage changing from 4.2 back to 4.14, I use a midpoint to calculate. Then that will become 4.17 squared divided by R. And then solve the equation, we can get the R becomes 0.4. It's a midpoint for calculate. You can use integration more detail, but that's fair enough. And then the voltage, I mean midpoint voltage divided by resistance becomes 8 amp, 8.6 amp. Quite a high current, right? But only for 1 minute. So it still be okay. So total power, the power rating for RB, you need to buy a resistor there, put it there. And the resistor power rating will therefore 36 more. This I squared, V squared over R, 436. So that's one scenario we can see the power rating for resistor quite a big, right? And the resistance roughly about this amount of the resistance, 0.48. And the other, we done that calculation. Another student will try to say, what do you think about this method? Is this method okay? Reliable? Would there be any methods to calculate the RB? What do you think about that? If your boss argue to decide the resistive balancing is very common job in the UV market, then is that the good way to design the RB, to calculate RB, to select the resistance for RB, to get the power rating for RB 36 watt of power? What do you think of this method?
This is how we calculate.
Yeah, that's one of the methods. Yeah. I think that there's some issue here. The thing is, we are using 10
Too
AH.
much power.
10 AH may be an issue because I know that when we fully charge the battery to 4.2 volt, it's 10 AH. But at 4.14, we may not have 10 AH because we fully charge from 0 AH, fully charged to. So the issue here, when I see this, what my student doing that? You see, we start from say 3 volt. And then 3 volt here. We start from 3 volt here, we charge to 4.2. And then the SOC from 0% to 100%, right? Then the curve is not linear, but it may be non-linear with something like that. So you see here, 4.14 here. The SOC, this point should be 10 AH. This point is 0 AH. Here, this point is not 10 AH. So it's too simplified to use this method to calculate. So what we like to do next, we use the second method. Now just thinking about the charge, right? The 4.2 reduced to 4.14. I just use it ratio. 10 ampere is the total, but using the change of here, the range operation 100% will be from 3 volt up to 4.2, and then our voltage now from 4.14 up to 4.2. So that means the actual changes will be 0.5H. That's the charge we decrease from 100% SOH reduced to 4.14. So that actually, if we assume the curve is linear, then we can know that we're going to reduce 0.5H from the system. 0.5H, then we multiply by 360 hours, become second, right? Become 1,800 Coulomb. So the system will try to remove 1,800 Coulomb from the battery. So then we try to remove 1,800 Coulomb from the battery within 60 seconds. So the current will be 30 amp. Okay. Once we know 30 amp, then we know the voltage. It's a midpoint voltage calculate 4.17 divided by 30 amp become the resistance 0.139 ohm. So if you consider the variation of the AH from fully charged 100% SOC down to 4.14 volt is not fully charged of AH, then the resistance should be this one we're going to use. And then beside the power will be higher now. V squared over R 4.17 divided by the resistance become 125 watt power. So that is much higher. Why is higher? Because we now have AH changes. It's not constant. Wider range. We need to remove more charge from the battery. In this case, the resistance need to be high power rating. So now then we got 125, and then 125 multiplied by 60 seconds, you know that 7,500 joules will need to be dissipated in the resistor. So now then we got two methods. What do you think? Which method will be more reliable? First method is simple way. We just assume AH is not being changed. But in fact, the second method, I think AH should be changed. So now then we can see that the method one will be the digital energy 0.6 WH is not accurate. Why is that? Because at 4.14 volt, the charge is not 10 AH. So this student underestimate the problem. It's fair enough. I mean, some people just using 10 AH. Second method, we try to say 10 AH will be reduced to 9.5 AH because we already charged. So using this method, you should have more accurate result. But the method 2 still has some problem. What is the problem for method 2? What do you think? The method 2 problem? Just now we use the midpoint voltage. But actually at fully charged, the voltage 4.2. And then when we reduce to 4.14, we have less AH. We should not use the midpoint to calculate. So the better thing to do will be calculate exact energy, like method 3. So now that we say at 4.2 volt, the battery cell is fully charged to 10 AH. And then at 4.14 volt, the battery already reduced by 0.5 AH. Yeah, just now we can see that in here, reduced by 0.5 AH, right? So the actual energy stored will be 4.14 multiplied by how much is being dropped, right? 9.5, right? So that is to say energy dissipated should equal to 4.2 times 10H minus the energy stored at 4.14 multiplied by 9.5. That's the actual energy being dissipated. That will be much more accurate. Do you get my point, right? With it. So the thing is, usually, if the voltage variation is not much, the answer may not be very bad, that much. But now then we're talking about 0.06 volt is quite a big number. Then the energy in here, V square over R times the time equal to 2.67 multiplied by 3,600. So we solve the equation again. We get R equal to 0.1 ohm. So compared to PS1, 0.139. You make certain changes. We need high power. So because what the method theory we are using, we actually calculate exactly about the power between the 4.2 and 4.18. So we need more energy to be dissipated. So the power rating becomes 160 watt. So you can see just now we're using this one, 125. Method 1 is equal to 36 watt. Method 1 did not calculate exact energy being dissipated. Method 2 improve a little bit because we calculate the AH. Method 3 will be more accurate because we consider the AH in two scenarios will be different. So the actual more accurate result will be 160 watt of power. So that's quite a big issue, right? A dumping resistor will cost you 160 watt of power. So you need quite a big resistor, but only for 1 minute. But sometimes if you have good cooling system, still quite okay. So the comment you can see that we have been using different methods to calculate the resistive balancing. All the method has a advantage and disadvantage. Method 3 will be usually more accurate. And we also see that the discharging time 1 minute may be far too little. If we can extend 1 minute to 5 minutes, then we can reduce the power rating. Because you see here, 160 watt is quite a big rating. If you try to make the balancing time instead of 1 minute become 5 minutes, I guess this one will be reduced by 5 times. That would be more comfortable. And also, we also need to ensure that the voltage, unbalanced voltage, cannot be 0.06 because too wide. It has too much energy, it will be dissipated. So once the sensor detects any unbalanced voltage, probably 10 millivolt, we can start to energize the unbalanced system. So your dynamic response for your comparator or test sensing will be quite quick. But the thing is, in the near future, when we have a huge battery, like ultra battery, super battery, then the energy content will be quite large. And also the charging speed, now they 30 minutes for fully charging. But in the future, only 5 minutes for fully charging. The changes from 0% to 100% will be so much different. So in this case, the resistor balancing will be a big problem because you need to handle high power. So you can see that today we're still quite okay, but every day, say yesterday, I hear that some company they can able to produce their vehicle finish charging within 5 minutes. Obviously, the charging speed really fast, and the voltage variation within 5 minutes they can vary 0.5 volt. So that's something we need to be careful in the future. So this tutorial just show us a few things. Firstly, different people have different methods for calculation. If you want to be more accurate, we need to make model exactly about the AH and voltage in each of the case before and after the balancing. Right? So that's something quite important. Any question? Here for the free method? So I show you free method, just show you how we approach the problem. But of course, all the free method is not accurate. The thing is here, we are using a linear method to do that. But in fact, I think the curve is not linear. Probably will be something like that. Okay. So in this case, this will not be 9.58, maybe slightly different depending on the curvature. But for this kind of the theoretical calculation, I think that would be fair in life. But at least in that tutorial, you know briefly about what kind of resistance we're talking about. What happened is the power weighting. How can we reduce the power weighting? Why the power weighting is so large, 160? That's not feasible for BMS. It's too high power. You can see that each voltage cell, we need 160 watt resistor. We got hundreds of the battery cell there. Then too much resistance. So the actual control will be using longer time for the balancing and much shorter duration. Not the shorter duration, shorter delta V. Because delta V 0.06 is too large, too much power losses. So the comparator should be respond really quickly within 0.01 volt, maybe even lower than that. Many of the commercial BMS, their voltage deviation is much less than 10 millivolt, only a few millivolt to be more reliable. Why is doing that? Because less millivolt of voltage deviation, we can have less power loss in the resistor. You get that? But of course, if we go for the MOSFET, we don't have that issue. Okay, anyway. So other parameter for measurement, we have been talking about the SOC, SOH, but for the BMS, we also need to measure the temperature called the state of temperature, SOT. So that means basically just measure the temperature, right? Another one would be state of power. You mean the power capability for battery are quite different for different voltage, different SOC, and different SOT. A different temperature, we have the BMS can estimate about the power rating requirement, the state of power for the battery. So by doing this, they will tell the BMS how much power can handle by the battery cell. So that means the system also need to get the SOP. Okay. Of course, SOF, state of function. So the parameter assess the ability of battery to deliver its rate power. It provides insight to the functional capability of the battery under various operating conditions. So FOF is include many things, not only state of charge, state of health, state of temperature, state of P. That they lump all this together, provide you the capability, the ability for the battery to do everything. Various things depend on your battery management system, what thing you need you to do. So that means the SOF can be able to say the transient torque, how much you can able to go up to, and also the vibration, everything. Many things can relate to SOF. So you can see that now we introduce more parameters. So of course, FOF may not exist in many BMS, but it happens in certain. Another thing would be people like to understand about the state of balancing, how good the balancing of the cell look like. So in here we have multiple cells, then we need to make sure that all the cells will be in uniform to each other. And then in this case, with our balancing circuit, like the active balancing, we need to adjust the duty ratio for the transistor in order to control the balancing. So when the state of balancing is unhealthy, then we need to turn on the duty ratio in more aggressive way to balance them. And then, of course, for passive balancing, then we can see that you only operate more look like overvoltage protection and overcharge protection. It more look like protection circuitry. You can see that even though we got the active balancing, we usually still have the passive balancing to protect the battery from the top voltage issue. So that is to say, for the active balancing with the MOSFET, we still need to put the passive balancing to protect from the top voltage damage.
So what do you mean by top voltage?
Top 4.2 volt. Yeah. So in case for any battery cell system, once it approaches 4.2 volt, we need to stop it. So that means the protection system will have that implement to protect from more than 4.2. But if you're using, so that means passive balancing appears in all the BMS. But if you want to do the active balancing, you need to do both. Protection plus the MOSFET balancing. And also the BMS also do the counting, cycle count, to see how many cycles the battery has been gone through. Because as you all know that the battery have a number of the lifespan are calculated by the number of cycles. So they will count it to see, to tell you, to estimate to you what is the lifetime left, remaining life. So this lifetime we usually will double check with SOH. Because SOH is another way to calculate lifetime to see if they do agree. If they agree, it's okay. If they do not agree, then we need to do some other estimation, maybe report for some maintenance to see any discrepancy. So you can see that BMS has a lot of the function. So you're also looking into charge and discharge rate, and then too high, too low, also need to be reported to record them. And then the thing is, all the charge rate, discharge rate highly relate to the state condition. So SOC, SOH, SOT, and SOB, all these things are related to the charge rate. So the computer inside will calculate, have a model to tell you what is the state of charge allowed in the system. And another thing the BMS will measure will be the cell discharge. Even though you don't touch the battery, it has its own cell internal leakage. That internal leakage will therefore depreciate the battery. Once the internal leakage lead the battery to a certain state, the battery will, if you're below the SOC equal to 0%, it becomes some damaging. You also need to monitor if the cell leakage is too much, then more than you expected, then that parameter will be determined by the BMS to tell the user or tell the manufacturer what shall have happened. So because if the vehicle parked there for too long, maybe a few months without charging, then the voltage may drop. So once it's dropped beyond a set point, then they would have some maintenance call or alert system. So that means cell discharge rate also be monitored. So anyway, finally, we want to talk about the future for BMS. For BMS in the future, we know that there will be solid-state battery coming out quite soon, or maybe some even high energy content, high power density will come out. So all the BMS need to be accommodate for these changes. At the moment, BMS are only for our existing battery 1C, 2C. But in the future, we have 5C, 10C. The charging rate is so fast. The SOC moving so fast, from 0% to 100% within 5 minutes. Then the response time for the BMS needs to be really quick. Just now you can see that little bit of 0.06 is very resistant by so much amount. So you can see the design for BMS, especially just like potassium resistor, need to be think about it carefully. So in the future, if you got high power battery, solid state battery, the charging speed so fast. In this case, we have a lot of adaptation, including we need a really good monitoring system for the solid state chemistry. We also need a good thermal management. The thermal changes will be really fast. And also we need to integrate them with all the EV powertrain, and also need to look into higher dynamic. The BMS is a much higher speed, not the normal 20 kilohertz, maybe much higher speed to respond for the changes. Any 1 millivolt changes, we need to respond really quickly. But 1 millivolt of changes may be within 1 second, not 1 minute. So that's the thing we need to look for the future BMS. So the charge will be high manufacturing costs. We need to try to standardize everything so that at the moment all the BMS are tailor-made to certain battery. But in the future, if we're able to make them, and standardize, everybody can use that BMS for different type of battery. That's a few tuning. That would be a nice thing to have. So that's the issue for the coming. So all our research are tailor-made to the future research, because we know that solid-state battery will come out in a few years in the commercial market. So you can see that the density will be a few times higher safety, but much faster charging rate. So BMS need to accommodate. So we also need to think about another new direction for BMS will be bidirectional charging. In the future, the battery is lost unidirectional. V to X, vehicle to grid, we can charge into the battery can be charged back to the power grid. So that is the issue we need to look into, right? So that's why the future BMS need to look into new road in V to X. So how to protect them, protect the grid, how to make it stable, then how to make the more benefit to the energy cost, resilient with the renewable energy, and also new revenue for the EV owner. So That is to say, your BMS needs to protect EV owners so they can make use of that battery, connect to the power grid, so the battery become one of the power wall or power bank for the power grid, for your house, for the whole power system. So the new role for BMS should be there. And then we're also looking in the modular approach to develop BMS. At the moment, BMS is all integrated inside the battery pack. But in the future, we can try to make it modular so that many modules can connect together, become your BMS. So just look like today many things are using modular approach rather than discrete components so inconvenient. So the good advantage will be we are able to make it suitable for all the vehicle and try to then this kind of new design can applicable to many different kinds of the vehicle. But the challenge will be how to make sure that all the different modules can communicate properly without any hiccup. And standardization from different manufacturers will be quite critical. At the moment, there's 100,000 of manufacturers for BMS. We all don't have any standard. So that's the issue. When we want to get a BMS, this BMS from manufacturer A is not compatible to manufacturer B. It's not compatible to battery A and battery B. So that's a big issue. So in the future, all the standardization model approach will be needed. Of course, in the future, sustainability second life application. In the future, we do a lot of the second life battery. How to make sure that will be done properly. How to use the BMS for the second life battery, because when the battery gets older, then the BMS is higher requirement. So including recycling, how to monitor the battery, would that be more dangerous, how to protect the temperature, everything. So that means the future BMS will be so important, including how we include the AI, IoT there, how to make the standard, how to collaborate with other industries. Not only EV are using BMS, even though many of the renewable energy, wind power, solar power, power distribution are using it. So the conclusion in here will be our BMS is getting more important. You can see that we not only talk about BMS today, but also talk about the BMS in the future, how BMS can look into the future, including modular approach, standardization, and high capacity to monitor the new changes in high energy. That's it. Any question? So I do have a book on this area, on the BMS. And anyway, so now then go to our quiz now. So please, you have 1 hour to do. You can start it anytime. Please.